Good morning, good afternoon, or good evening. This is the first question of the Step 3 2024 paper. As with all of these walkthroughs, you should have had a go at the question beforehand. Watching someone else's solution spoils almost all of the value that you can get out of the question by tackling it yourself. Fighting through the subtleties is what improves us as mathematicians. And we're going to start with this first question. Normally, question ones on all the step papers are slightly nicer than the rest. So let's see if this follows that trend. We have been given some conditions, some notation. Sn is going to be the sum of 1 over r squared, and we've been allowed to assume that the limit of this sum is pi squared over 6. Quite a surprising result. The sum doesn't appear to have anything to do with trig or to do with circles, but there's a pi squared in it. And let's tackle part 1 straight away. Starting off with a partial fraction style thing. So let's start with the side that looks slightly more complicated. The left-hand side is the one that more easily looks like it can be simplified. And the only real sensible thing we can do here is make a common denominator. So the first one times top and bottom by r squared. The second we're timesing top and bottom by r plus 1. And the third one just needs an r plus 1. So combining all those fractions together, we have an r squared minus r squared plus r plus 1 from the final, all over that denominator of r squared, r plus 1. And now the things that cancel, the r squared cancels the r squared, the r cancels the r. And I'm left with exactly what was required. Equals right hand side as required. So now, how are we going to use that? We now want to show that this sum is equal to that thing. So the sum from r equals 1 to capital N of this thing, well, from what we've just proven, this is the sum of 1 over r plus 1 minus 1 over r, and I'm going to separate it in this way because I'm already recognizing that that first sum is basically your method of differences. It's what's called a telescoping series, which basically means lots of things end up cancelling out. So that's going to be a half minus 1 over 1 as the first term, plus 1 over 3 minus 1 over 2 for the second term, all the way to the final term, which will be 1 over n plus 1 minus 1 over n plus that sum left over. But if you notice here, lots of things cancel out. This half cancels with the half in the next, the third cancels with the third in the next, all the way up to the 1 over n from the previous cancels with that minus 1 over n. So just checking in the order that the answer's given it, we still have the sum of this 1 over r squared. We've got the minus 1 plus the 1 over n plus 1 from that telescoping series that got left behind, that didn't cancel. Now let n go to infinity. So now this sum is going to tend towards, well, the first part by the statement given to us, the sum of 1 over r squared becomes pi squared on 6 minus 1, and then that final term as 1 over n plus 1 tends to 0. We're letting n become huge, so the denominator is becoming huge. 1 over a huge number gets closer and closer to 0. Well, that was a very quick first part of the question. Let's see how we can adapt those methods going forward. So now it's asking us to find 1 over r squared, r plus 1, r plus 2. So I could take the result up here and multiply that whole result, or divide that whole result by r plus 2. Is that going to help? Well, this will be r plus 1, r plus 2 on the denominator here. This will be r plus 2. Not particularly helpful. We won't get that telescoping nature that we had before because the denominators aren't consecutive. This one really worked because this matches with the next term in the second part. And then this sum also doesn't really work. But we can take the idea that we had in that part I, which is that partial fractions. So let's try and find the partial fraction form of this 1 over r squared, r plus 1, r plus 2. And the partial fraction form is going to be something over r plus something over r squared plus something over r plus 1. I need to use a different something. Plus something over the r plus 2, which if I multiply everything up says that 1 equals all the things that were missing from that first one, plus b lots of the r plus 1, r plus 2, plus c lots of, that needs an r squared and r plus 2, plus d lots of, that needs the r squared and the r plus 1. So now let's try and find these coefficients. If I let r equal 0, that cancels everything which had an r term in. So that's 1 equals the a's disappeared, the c's and the d's have disappeared. So then that's just b times its things. So that equals 2b, i.e. b is a half. I can let r equal -1 for a similar situation. So now 1 is equal to the a disappears, the b disappears, the d disappears, but the c survives. The c survives with a coefficient of 1. So that's just c equals 1. We can let r be -2. That kills the a, kills the b, kills the c, leaves behind the d. With -2 being subbed in, the r squared is 4. The other thing is negative, so that's -4d. Which means d is -1/4. And then finally, we need to still find the a. Probably the best way to do that is to look at the highest power, which is the cubed term. So looking at the cubed term, there are no cubed terms on the left. There is a single a cubed plus c plus d. So therefore a has to equal -3/4. Okay. Well, a couple things to notice a couple things that I noticed straight away. These two parts are the parts which I kind of wanted to telescope, but they aren't going to. The c is 1 and the d is -1/4. So they're not going to telescope particularly nicely, but maybe the a part can telescope with the c part, and the c part can telescope with the d part at the same time. And that indeed is possible, because I could write c as 1/4 plus 3/4, which feels quite stupid, but that then matches the quarter with the d and the 3/4 with the a. So I'm actually going to write it in that way, slightly strangely, but I can now say that this thing is equal to 3/4 of the c minus the a plus 1/4 of Now, which ones are positive? It'll be the C things that's positive again, r plus 1 minus the D, r plus 2. That's covered all the A, B, the A, C, and D, plus half 1 over r squared. Okay, nice. So now we're actually wanting to work out the sum of this. So summing up to capital N, we got the sum from 1 to n of this r squared and other stuff equals. Now let's try and be efficient about this. We've got 3/4 of. Now those, you'll start with a half minus 1. Actually, that's identical to the sum that we did up here. So it's just going to give the identical answer, which was the minus 1 plus 1 over n plus 1 plus 1/4. Now this next one we need to be a bit more careful with. This sum here, when r is 1, it's a half minus a third. When r is 2, this is a third minus 1/4, plus all the way up to when r is n, that's n plus 1, that's 1 over n plus 2. Things cancel, the third cancels, the quarter cancels all the way up. The n plus 1 will cancel with the previous, and that's what I'm left with. So I'll be left with a half minus 1 over n plus 2 plus half the sum from r equals 1 to capital N of 1 over r squared. It's probably worth simplifying and cleaning this up a little, although we have, in terms of Sn, well, this is in terms of Sn. Sn is that sum on the end, but it is worth cleaning up a little. We've got minus 3/4 plus an eighth, so that's 6/8. So that's minus 5/8 plus 3/4 of the n plus 1 minus 1/4 of the n plus 2 plus half Sn, putting that sum in as what that sum actually is. And we've now want to evaluate the limit as n tends to infinity. So as n tends to infinity, the 3 over 4 n plus 1 goes to 0 for the same reason described before. The 1 over 4 lots of n plus 2 goes to 0, and Sn goes to pi squared on 6. So this sum from 1 to infinity of that fraction is going to equal, now what's left behind, the minus 5/8 plus now pi squared on, not on 6, because I've got the half in front, pi squared on 12. Now I'm marginally worried for a moment, just because I've got this minus. Is this positive? I quite like to hope that this infinite sum of positive fractions comes out as a positive thing. Well, if I do some very rough calculations, pi squared is very roughly 9, so on 12 is very roughly 3/4, which is 6 over 8. So yeah, this thing does come out to be positive. A good little mental check that you haven't done something too strange with the calculations here. Okay, that's part 2 done. So now part 3. We're now trying to show another sum is linked to another sum. Well, the right-hand side is actually something we've already dealt with. So the right-hand side, which is can be written as 2 lots of the infinite sum from 1 to infinity of r squared on 1 over r squared, r plus 1 minus 1. I've taken the 2 out, so that's going to be 2 lots. And I'm using my solution to part I here. That sum is 2 lots of pi squared on 6 minus 1 minus another 1. So that's a third pi squared minus 2 minus another 1 minus 3. Again, mental check. Is this thing positive? Yeah, pi's a bit bigger than 3. So a third of pi squared is definitely going to be bigger than 3. Now the left-hand side is going to be a little bit more of a challenge. Is there a trick I can apply? Again, I could go back to part I and think, can I times or divide everything by r plus 1 to make the right denominator? Would that do anything for me? And actually, no. I was thinking we've got the r plus 1 here, we've got the r squared here, that'll be r plus 1 squared. No. It feels like I don't really want to do the work again, but it feels like another partial fraction. And considering this question's been quite nice so far, let's keep assuming that it's quite nice. So let this 1 over stuff. Now this is quite an awkward partial fraction. So we need both the a over r and the b over r squared, the c over r plus 1 and the d over r plus 1 squared, which may mean things either become much simpler or much worse because of this weird structure. Already I know that I'm going to have to worry about how I'm getting all these coefficients, because I've only got 2 values of r which are clever in some sense. The r equals 0 means that 1 equals r equals 0 is, destroys the a, c and d terms, so that's equal to, well, just b times 1 squared. I can let r equal -1. The -1 is going to get rid of the a, the b and the c terms, so 1 equals d. And now I need to be clever. So if I look at the r cubed term, there's no r cubed on the left. We're going to get an a and a c. That's unfortunate, because that doesn't just give me one of them straight away. What else could I do? I already know the b and the d. I could look at the constant term, but that would just give me the b. That's the same as looking at r equals 0. I don't really want to look at the squared term because that requires a bit more thought. I could look at the linear term. Yeah, the linear term actually is a little bit smarter, because the linear term, there is no linear term here because we're times everything by r squared. There is no linear term on the d either. So this will actually be a link between a and b. So the linear term on the left is 0. If I were to imagine expanding out the r plus 1 squared, timesing by r, the linear term is just an ar. And for the middle one, we get a 2b. If you were to imagine expanding out that r plus 1 squared, which tells us what a is. A has to be equal to -2, which then also tells me what c is. C therefore has to be 2. And this is actually really pleasant, because now we have the a and the c causing this telescoping nature that I require. So now the sum from r equals 1 to n of this r squared r plus 1 squared 1 over it can be written as 2 lots of the sum from r equals 1 to n. So this is my a and my c. 1 over r plus 1 minus 1 over r plus, now the b and d terms, this is the sum from r equals 1 to n. Let's actually use the notation they have. So that's just going to be Sn. I'm summing up to n plus, and now the sum of the d's, we can be actually, the d thing, we can actually be quite clever, because we're summing from r equals 1 to n, so we're summing r plus 1 from 2 up to n plus 1. So this is actually the sum to n plus 1 minus that first term. And you should justify that carefully. I'll do it off to the side here. The sum from r equals 1 to n of 1 over r plus 1 squared is the sum from the denominator. And I'm just thinking about the denominator here. The denominator is going from 2 squared up to n plus 1 squared. So that's Sn plus 1. But we've not included the first term, which is 1 over 1 squared. So I should justify that to make sure that I'm not sneaking anything by the examiners. So this is equal to the telescoping idea again, 2 lots of, now we've got the minus 1, and this, again, this is the same sum we've done multiple times now, plus 1 over n plus 1 plus Sn plus Sn plus 1 minus 1, and then let n go to infinity. So the sum from, so this is now the left hand side, it's the sum up to infinity of -2, because that fraction, the 1 over n plus 1 disappears, plus pi squared on 6. Now the nice thing is, even if you add 1 to that denominator thing, we still get a pi squared on 6. The limit is still the limit, even if you got there just one step further. I didn't actually put the thing we're summing next to my summation. So this is equal to pi squared on 3 minus 3, which is exactly what, which equals the right hand side as required. That's why I did this calculation up here to refer back to. Really nice question, actually. Really fits with the question 1 is quite pleasant, just do it. And the only real clever thing to have noticed here is the method of differences. The fact that we have these telescoping series where part of the next term cancels with some of the previous, and the fact that we actually did this exact sum here in every part of the question, and every part of the question used the same idea of partial fractions and things cancel really nicely. So hopefully that was a useful question to go through, to see how the nice questions can sometimes just be nice, pleasant all the way through. Hopefully that was helpful, and please do watch the rest of the videos in this series for similar questions from Step 3 2024.